Okay, everybody, we are on page 6. It's the mechanism page. We're going to read all of these instructions because there's probably some really great stuff in there. So we have Mark and Nick that are beginning students in the OChem lab, and they're arguing over how to make 1-methyl 1-bromocyclohexane. Mark wants to start one way with 3-methylcyclohexane here, and Nick wants to do it with methylene cyclohexane from the beginning. But their lab mate, Kat Ayan, tries to break up the fight and tells them that the alkenes could really give the same product. We want to give an idea of who's the most correct person, and then write that on the back page. But I'll just highlight it for you. We're going to do separate arrow pushing mechanisms for both reactions. All right, so this is all laid out for you in this bubble up here. So this is really just an overview of everything that's stated above. So we're going to go through what I'm calling Nick's mechanism first, where we're starting with methylene cyclohexane. So what we have first, I'm going to make some notes. In this addition, hydrohalogenation reaction, the alkene is going to be a really nice carbon nucleophile. You have electron density here. That pi bond is delocalized, and so those electrons are waiting for a nice electrophile to come along. And then we can see by default, or just knowing that this is an acid can help you remember that hydrobromic acid is an electrophile. We start at the nucleophile and end at the electrophile, specifically the hydrogen of that compound, because the bromine is pulling away electrons. So there actually is a dipole initially, but this bond in this case now breaks. Now, what we could do here, as maybe you knew this first step, maybe you didn't, but we could make a nice little list of bonds that we should expect to be broken and formed. I should have probably done this before I wrote some arrows, but well, I didn't, so here we are. The bonds that are broken, if we look from starting material to product, we see that this was a double bond, but now it's a single bond. So we have this one bond, carbon-carbon pi bond, being broken. As we are seeing during the course of this mechanism, there was an HBr bond in the starting material, but no HBr bond in the product. So that's going to be our second broken bond. In terms of bonds formed, we had just two hydrogens connected to this carbon out here. And now over here, we have 3. So we formed a carbon-hydrogen bond. This is where all the structural stuff that we did in the beginning of the class is really coming into play, of knowing how to interpret these structures. And then the other bond formed is the bond between the carbon and the bromine that you see there in the product. Alrighty. So in this first step, what we've done is we have formed the carbon-hydrogen bond once we show that in the intermediate, so it'll be good. And then we've broken the HBr bond. I think I wrote it correctly over here. So we are breaking the HBr bond. That's what those arrows mean. And the starting and ending point of those arrows is super duper important. We have the same single bond structure in the ring. We have just a single bond right here. And this is where we have a choice of where to put the hydrogen. This is the new hydrogen. Yes, there are still 2 hydrogens there, but this is the new guy. And because this carbon that's tertiary didn't get any back, it is now positively charged. We have bromide floating around. By the way, I don't need to draw these things, so I'm just going to leave those out. We also have the bromine, that was the leaving group in that first step. And it's going to be the nucleophile in the second step, whereas the tertiary carbocation is the electrophile in the second step. So we're going to start at the nucleophile, electron rich, and at electrophile, electron poor. That gets us to our product. We have formed the carbon-bromine bond, and I should have put a check that we broke the carbon-carbon pi bond. Okay, so that's the first mechanism. We'll just leave that alone. Now over here, we should have a similar set of arrows, so I'm not going to go through and identify quite as much in terms of bonds broken and formed, except what I will say is that we want to make a couple of notes on what is different. So here we have hydrogens that I've indicated on those individual carbons, and I'm doing this for the sake of bookkeeping. So there's a pretty big difference here that we have, 2 hydrogens added, what looks like added across the double bond, and then at first glance it looks like that hydrogen is just replaced for a bromine, but you don't know one of those reactions, and actually that is not a real chemical reaction that happens, and you really just want to stick with what you know, so go with what you know. What we know is what we did above. So I presented the simpler, more expected typical mechanism at the top, so we're going to start there. We're going to start at the double bond, end at the hydrogen, kick those electrons onto bromine. That gives us an intermediate with a secondary carbocation. That's still methyl group, and the newly added hydrogen here. And yes, there is still that other one that came along for the ride. It is possible also, and I'll kind of address this more in the second line, that the carbocation went here. We have 2 hydrogens here, and if we want to pull out every single hydrogen just in that area of interest, then that might be useful. All right, so that's what we're kind of stuck at, is that we have these secondary carbocations, and it's not really clear how the bromine is going to get to the tertiary carbon. So that's sort of the weird thing that's going on. So instead of trying to figure it out in a forward sense, we're going to work our way in reverse. This product must have come from the tertiary carbocation. So this must have been the last intermediate where the bromide came in and attacked here. That had to be the last step. So we work ourselves in reverse a little bit. That's just the only way we know how to make those carbon-bromine bonds. So now we've simplified our problem. The question is now, how do we go from here to here or from here to here? And the thing that's going to be really helpful here is keeping track of your hydrogens in the zones of interest. And the zones of interest just being here, that tertiary carbon, and then the remaining hydrogens in, once again, the zone of interest just being like where the reaction happens. And here we're going to track that in this first one, this here one here on top, we have a hydrogen there in the tertiary position, and we don't have a hydrogen here. It's just not there. It doesn't have to be implied or shown, but we do actually have 2 hydrogens on that carbon. So that's going to be pretty significant. We're going to want to do what we call a hydride shift. Right, that applies to both of them. And in these hydride shifts, we're going to transfer that tertiary hydrogen over to the carbocation, and that hydrogen is going to bring its electrons with it. So here we go. Very important, I'm going to really zoom in on this, that we start at the carbon-hydrogen bond and we end at the carbocation. So just once again, it means that the CH bond breaks and the hydrogen moves to, in this case, a secondary carbon, and it brings its electrons with it. And the thing that could be helpful for that is a hydride is a hydrogen anion, H- with a lone pair. So that's one way of doing it. That's a pretty good way. But if you happen to have drawn the carbocation on that secondary carbon, you can still make it work. And hydride shifts tend to not happen too far away. But if you're trying to figure out how to make this happen, you could do one of those. This is probably preferred, but this way still tells this way up here at the bottom still tells the same story that we talked about up here, in that the carbon-hydrogen bond is breaking, moving that hydrogen to the secondary carbon, thus leaving you with a tertiary carbocation by default. And that is how you get to your product. Now, in terms of who was the most right, well, both of them, both Mark's and Nick's ways, can get you to the tertiary bromide. But Kat was saying that both of them could theoretically give the same product. So I would go with Kat on this one, that they theoretically gave the same product. If you wanted to choose like a better way of doing it, you could maybe even argue that Nick was right, because if you're not going through a carbocation intermediate, you probably have just one product, whereas this one, although presented as just one product, it is possible that you have other products as a mixture. right? You may have had bromination at either of those secondary carbons, so it is possible that you could have gotten a bit of this product. You could have gotten a bit of that product. So between Mark and Kat, it's a pretty close call, but theoretically they could give the same product. And I hope that whole mechanism stuff was useful. And thank you for watching and happy studying.